Okay, so combustion analysis. So we have this compound right here that we know that it contains carbon, hydrogen, and oxygen. If we heat 0.513 grams of this compound or this acid, we see that we get 0.501 of CO2 and 0.103 of H2O. And it wants to know the empirical formula. And then the second part is it gives us its molar mass and wants to know its molecular formula. So we're going to take the CO2 first, and we're going to say 0.501 grams of CO2. Okay, and then I want to get that to moles, so I'm going to divide by the molar mass of CO2, which is 44.01 grams per mole. And in a molecule of CO2, in 1 mole of CO2, I know that I can have 1 mole of carbon. Do you agree with that? In every mole of CO2, there is 1 mole of carbon. So we're going to use that molar relationship or that stoichiometric relationship. So that would give me, when I do that math, 0.0114 moles of carbon. Okay, now I'm going to do the same thing with the water. I'm going to say 0.103 grams of water, and I'm going to divide by the molar mass of water, which is 18.02. And for every 1 mole of water, how many moles of hydrogen do I have? 2, because of that little subscript, so 2 moles of hydrogen. And looky there, I get the same answer, 0.00114 moles of hydrogen. Okay? So I have my moles of carbon and my moles of hydrogen. How can I calculate how much oxygen I have? So what I'm going to do is I'm going to do a calculation over here and multiply by the molar mass of carbon, which is 12.01 grams per mole. And when I do that, I get 0.137 grams. I'm going to do the same thing for hydrogen. What do I use for the hydrogen's molar mass? I do not. That's why I asked that. Because hydrogen is bound up in a compound, it's single, so it's 1.01. Okay? You only use the molar mass of diatomics when they're completely by themselves. And that is probably the most common mistake on these type of problems across the board every year and on the AP exams. So you're going to just do the molar mass of 1 hydrogen, and then that comes out to be 0.115 grams of hydrogen. So now I can figure out how much oxygen we have by subtracting those numbers from the original amount, because remember, I only have carbon, hydrogen, and oxygen, so according to the law of conservation mass, it has to equal the total. So I'm just going to say 0.501 minus, and then I would add those together, 0.5 grams, and then I would get that I have 0.365 grams of oxygen. Okay? So if I convert that into moles, now I can see my ratio.
Why did you subtract it from 0.501 instead of 0.5?
Oh, because I wrote down the wrong thing.
Oh.
That's why. Thank you. On my paper, I have 0.513. I just looked up and saw that number. Sorry about that. So there. And that will actually add up to 0.365. So now that I have the oxygen, what do I need to do to oxygen? Convert it to moles. So I would divide by 16 and get my number of moles as 0.0228 moles of oxygen. And now I'm out of room, so I'm going to let y'all catch up and then I'll erase and keep going. Okay? So now I've got everything into moles, so what's my next step? Divide by the smallest. Okay? So I'm going to do that in the next step because I'm out of room. But I think people are still catching up on writing. These problems are a lot of work. Yeah. But I'm weird. I like doing them. They're fun. I don't know. I thought they relax my mind. When it gives me something to focus on. I'm quite ADD. Okay? Is everybody caught up with that? Okay, I think this erases it. Yes. Okay, so then for carbon, hydrogen, and oxygen, we can say we had 0.000114, 0.0114, 0.0114. Oh, no, sorry. I just really like that number, apparently. 0.0228. Okay, so now I'm going to divide everything by the smallest. So I get 1, 1, and 2. So my empirical formula would be CHO2. So that would be my empirical formula. And if I was to do this on the AP exam, I would go ahead and like box it so they know that I knew what I'm doing. The clearer that you can make it when you are doing the FRQs on the AP exam, the better it is for you. Because if they can see it real clear, most likely they would go, oh, they got the answer. And they'll look and see if you have work that matches. But if they have to go digging around and seeing what you did and see if you can figure out, that's more, and they're more likely to find any mistakes. So try to make them as clear and easy to grade as possible. I don't know any of you well enough to, well, I know some of you well enough to know about handwriting. If you are someone who has really hard to read handwriting, I'm going to try to say this nicely, you need to try to make that a little bit more legible on the exam, okay? Because the graders are grading, a grader grades one question throughout the whole thing, so it's consistent, and they're grading, you know, thousands upon thousands upon thousands, and if you can make it nice and neat for them, they're more likely to be a little bit, I think, a little bit more lenient with you than if you can't, if they can't read it, they're only going to try so hard, and then you're like, I can't read that, okay? So that's our empirical formula, so molecular formula, okay? When I taught this, I don't know if Miss Lawrence did this, but I would teach them to show your empirical formula like this, showing that it's an empirical formula, and then we would go solve for this N, okay? But basically, the way you go from an molecular to empirical to molecular is that N is going to be equal to the molecular form, the molar mass, I mean, over the empirical mass. And remember, the empirical mass is calculated just like molar mass. It's just for the empirical formula. Okay? So I'm going to erase this because I'm running out of room again. So we came up with the CHO2. You do not have to write it this way, but I find it an easier way to explain to you how to get from empirical to molecular. So it gave us a molar mass of 90.04, and then we're going to calculate the empirical mass of the CHO2. When we do that, we get 45.02, so it comes out to 2. So now we take that 2 and we plug it in there, and we get our empirical formula to be C2H2O4. Questions? Okay.
That's the empirical formula?
This is molecular. This is like, because remember the difference between the molecular and the empirical is the simplest ratio, the simplest one it could be, okay? The empirical formula, I mean the molecular formula is what it really is. Yes?
So the 45.02, that's the...
That is the mass of this.
Okay, yeah.
And you calculate it just like you do molar mass. It's just not called molar mass because that's not a molecular formula.
Okay.
Yeah. But it's calculated the same thing. Add them up on, 12.01 plus, it's the same thing. Okay? That's the same thing. Okay. Earlier today, the journal question, I had put up a formula up there, and I wanted to ask you, I asked you what the empirical formula was. Did y'all get an answer for that? I think I had done C4H12O2. Different problem. This is totally related. This was a journal. So that's its molecular formula. What would its empirical be? C2H6O. So you just reduce it, basically. Reduce it. Yes.
So why at the very beginning do you multiply it by its molar mass? Or
You mean divide by its molar mass?
Yeah, like whenever you get like the moles of carbon, why are you multiplying it by 12.01?
Oh, because we need to know what mass of carbon we had in that compound and what mass of hydrogen were in that compound, so that we could see what the mass of oxygen is. Because we can't do oxygen the way we did carbon and hydrogen, because when you burn oxygen, it's going into both compounds. Okay? And so we can't, and also some of that oxygen came from, from burning it. So that's why we have to do it that way.
And then you get the mass of the oxygen so that you can get it to moles.
So then we can compare the mole ratios. Okay. Yeah, that's the way you do it with the combustion analysis. The other ones, they sometimes, if it's not doing it through combustion, they just give you the percentages, or they might just give you how many grams are in the compound. Then it's just straightforward, you go. But in a combustion analysis, when it makes CO2 and H2O, you have to do it this particular way. And this was one of the things that they stressed to us in my class this summer. They said, make sure you're doing some combustion analysis with them. So one of those things, it may show up on the AP exam, it may not. I mean, sometimes it does, sometimes it doesn't. So it's all a gamble what we think is going to show up. So
but it's massively important.
It's massively important. Okay, so that is pretty much the last thing we're doing on empirical molecular formula. Tomorrow we're actually going to do a POGIL activity where y'all are going to get together in groups and practice this more. So I didn't actually give you like a worksheet on it, but y'all are going to do this together tomorrow in a group activity. Probably about 3 or 4 in a group. Okay. Okay. Sorry about that. So that brings us to chemical equations, maybe. Hopefully you know that the reactants are before the arrow and the products are after the arrow. And the arrow means yields. And then, of course, we balance them. Must have the same number of both sides. This is all very much a review. It's going to be important in here to use the physical state, solid, liquid, gas, and aqueous. Okay, especially when they're asking you to tell exactly what's happening in the reaction. And when we get to KSP, you need to know that we don't include solids and stuff like that. So it's going to be important to have, they're tedious. I hate writing them behind them, but they are important because it kind of lets us know what's going on in the reaction. So balance equations. If it's a normal regular equation, we just balance the charges. If it's a redox equation, then we got to do that one differently. Okay, but we'll do redox on chapter 4, not here. Okay, so here's an example. How would we balance these? I think it balances it for us. 2 aluminum, 3 chloride, and 2 AlCl3. This is all pretty straightforward. Hopefully, everybody's good with balancing, right? Yeah. I'm not going to give you a worksheet on how to balance equations. Okay. All right. Yeah, hopefully we know how to do that. So this one, you have to be able to write them. That's something we didn't practice a lot. Yeah, we did actually practice that. Of writing it from the words. You got to just be able to read what it says. So this one would be very easy. pH 3 combusted in air. So that means I'm going to add what to it? Oxygen. Oxygen. And then it makes water. And it says it's gaseous water. Plus solid P2O5. And so you would write those. That's going to be a gas, of course. And then they told us that was a gas. And then we need to balance that. So what would we do to balance it? Easiest thing to do is I see this 2 P2. I would go ahead and put a 2 there and start there. So that gives me how many hydrogen now? 6. So I'm going to throw a 3 there so I can have 6. And then how many total oxygen do I have now on the product side? 8. So I need to put a 4. So it doesn't matter where you start, just start. Sometimes you can look at something and go, I don't know how to do it. Just start balancing something and see what happens. I mean, all you're going to do is start over if it doesn't work. NH3. And it says gas. So we got G is passed over hot liquid sodium metal. Not something you usually write as a liquid, but it does say it's a hot liquid. Hydrogen gas is released. We know that that is a gas. And then solid, NH, and we do an S. And then we have to balance that. So how are we going to balance that?
Add a 3 or
Add a what?
add a 3
I
and solid.
don't need a 3.
Huh?
I don't need a 3. Add a 2 to NH3. Is that what you said? Yes.
Then add a 2 to the NH2.
Add a 2.
And then add a 2 to the
And then add a 2. And I'm done. Yep. All right. So then that brings us to stoichiometry. Yay. Mole ratio, remember, is required in every stoichiometry problem, and it's always the moles required over the moles given. That's how you get from what they gave you to what you're trying to get to. Okay, so I have, and if you were in my class, I said moles of the unknown over moles of known is another way to look at it. So this one says, what mass is formed when 5.38 grams reacts with water according to this equation? So of course we always start with what it gave us. So 5.38 grams of lithium nitride. I need to do what? Divide by the molar mass. 34.83. 1 mole. And then I need the mole ratio. This is an easy one. It's 1 to 1. When it's 1 to 1, you still need to write 1 to 1. Don't just go, oh, it's just, yeah, don't ever just assume they know that it's, always write it. Here's another thing. If you are crunched for time and you're doing a problem and you can't figure out how to balance it, go ahead and still write the problem and just use a 1-to-1 ratio, because they might take off points for the mole ratio, but you get points for knowing what you were supposed to do. Okay, so if you happen to get a really hard one, and then we have to go to NH3, and so we multiply by the molar mass of NH3. Is this ringing a bell?
Yes.
Good. And then that works out to be, I need 3 significant figures, so it would be 2.63 grams of ammonia. So hopefully that rings a bell. Yes?
How do you get the mole ratio again?
Oh, from the balanced equation. Yeah. So there's nothing in front of them, so it's a 1.
Okay.
But if we were trying to go, say, from lithium nitride to lithium hydroxide, this would have been 1, that would have been 3 on top.
Okay.
Yeah.
Do we have to balance the equation before that? Like,
Sometimes. Yeah. Here's the thing about that. Always check to see if the equations are balanced. Don't just assume that it's not. Now, if it's written down and you already see some coefficients in front of it, then they balance it for you. But if there's no coefficients, double check that it has been balanced. Okay? And when we get to redox, you work redox stoichiometry problems the same way. You just have to balance them differently before you do a redox. Redox are my favorite. Okay. Limiting reactant. Do you want me to show you the animation? I don't know if it's going to work through the dossier, but I'll try it. But remember, with limiting reactant, the easiest way to do it is they're going to give you 2 masses, and you work the problem twice, and then whatever gives you the smallest answer is your answer. Okay? If they ask you what a limiting reactant, which one the limiting reactant is, and they're not asking you in terms of one of the products, just pick a product to work. Because either it doesn't matter if you pick product 1, 2, or 3, you're going to get the same limiting reactant the whole time. Pick the easiest one. Like, don't pick a real, like, complicated high mass or whatever. If there's water, pick water, because you all know what the molar mass of water is at this point in your life, right? Anybody remember? 18.02. If you don't remember, you'll remember very quickly. Because those ones we do all the time, you just kind of get them. Let's see if the animation works from here. I don't know if it does. Oh, this is, yeah. Y'all don't need to go through this, do you? Make a sandwich. What are you going to run out of? Do y'all want to read this or go on? Yeah. Okay. So, remember I told you about particulate. I want you to draw, if you were to draw this reaction, assume the reaction goes to completion, and I want you to draw the resulting particles in the right-hand box. And then tell me which one is the limiting reaction. Okay? And I will give you a hint. Count up the number of particles in the before box. I'm recording. And then hopefully your drawing will look something like this. You should have 3 compounds drawn together, or 3 ionic things drawn together, and then you should have 2 circles, because you have 2 circles left over. That's your excess reactant. So in this case, the limiting reactant would be X, because you run out of that. Okay? Any questions on that? All right, this one is limiting reactant. It's an easy one because it's just moles. It says how many moles can be produced by this reaction if you have 1 mole, 2 mole, and 3 moles of each of your reactants. Okay, so these are the easy ones because we don't have to even go to molar masses and all that stuff. So we're going to start out with 1 mole of the Fe2S3, and the mole ratio would be 2. And I know it's tempting to just go 2 moles, 1 mole, or 2 moles, whatever, but please write it out for the AP exam. And then that works out to be 2 moles. And then for oxygen, or no, hydrogen's next, 2 moles H2O. And we have 6 moles H2O. 4 moles of FeOH3. That works out to be 1.3 moles. And actually, if we were doing it with significant figures, it'd be 1 mole. But this is just asking us how much we can produce. So actually, with our answer, we would need to put in the right sig figs. Oh, no, it's 0.0. Never mind. I lied. And then 3 moles of oxygen. And that mole ratio is 3 moles of oxygen to 4 moles of the iron oxide, or iron 3 hydroxide. And that works out to be 4 moles. So the most that we could produce would be 1.3, and that's because water is limiting. Hopefully you won't ever have to do one that has 3. Usually it's just 2. But you always pick the smallest one. There are some, if you're watching a tutorial video, there are some that teach you to do it in terms of the other reactants and figure it out that way. But I feel like that's a more complicated way. We know how to do a stoichiometry problem, so we can just do it that way. Okay? Okay? On the next one, in the interest of saving time so I can finish off the notes, I'm going to give you what the answers are so that you can go and work the problem and see if you get the right answer. Okay? Is everybody done writing this before I move on? Got it? I don't want to move on with that. Yeah. Okay. So on this one, when you work this out, your final answer, when you get this, is going to be 24 grams. but I won't tell you which one's limiting. I'll let you figure that one out. But if you get 24 grams, then you did it correctly. Actually, I'll give you both of them. One's going to give you 29.9, one's going to give you 24. So the one that gives you this is going to be your limiting. Because you know that's a good practice one for you. So then very quickly, let's finish off with percent yield, which is a calculation that you're going to probably refer to back a lot in labs, because I'll say calculate your percent yield, or percent error is something different. But percent yield, if you remember from Chem 1, is your actual over theoretical. And where do we get our theoretical yield from? Say it. From your stoichiometry problem. Yeah. Any stoichiometry problem that you work is your theoretical yield. That is, in theory, how much we could get. In actuality, you never get that much. Your actual yield is always smaller than your theoretical yield. Very rarely does anything get 100% reaction. Okay? And so your actual yield has to be given to you. Okay? And you want to look for words like obtained, isolated, you know, that kind of thing, to make sure that you know what you're at. They don't always come out and say your actual yield is this. They might say it was obtained or isolated or whatnot. Okay, so here we have this reaction, and it says the reaction of 1 mole with an excess of Cl2 was given to you that 83.5 grams of the carbon tetrachloride was obtained. What is the theoretical, actual, and percent yield? So we have to write the balanced equation for this. So we are reacting CH4 plus Cl2, and we are making CCl4. Where does the hydrogen go? Yeah, it's going to be released as a gas. So then we balance that, and we put 2 here and 2 here. Okay? So we start with our 1 mole of CH4, and for CCl4 it's a 1-to-1 relationship, so it's 1 mole of CH4, 1 mole of carbon tetrachloride, and then we multiply by the molar mass of that. I like it when we start with moles. It makes our life easier. It saves a step. And we need 3 significant figures from the 1.00, so we would write that as 154 grams of CCl4. That is our theoretical yield. So then to get percent yield, we would do actual over theoretical times 100. So they gave us 83.5, and we said we should have gotten 154, and I forgot to put that in sig fig, so I think it should come out to be 54.3, but if you get a slightly different number, I was doing this at Starbucks and I wasn't paying attention to sig figs, so it might be a tiny bit different. So that would be our percent yield. Any questions? So we just basically did in one day what it took y'all like a whole unit in Chem 1. This is why it's important to learn it in Chem 1. Which is why I'm also giving you practice, okay? And because some of you are like, I got this, I don't want to practice, and then some of you haven't seen it in a while and you want more practice. So I don't want to make the ones that have it down, I don't want to make them like practice more than they want to. After the next unit, when we get to that, it will be new stuff, and then we won't go so fast.